Welcome to Mrs. Z's Chemistry. In this lesson, we will learn how to calculate the equilibrium constants. As we learned in the last lesson, each chemical reaction has a different ratio of products to reactants that exist at equilibrium. Some reactions create more products, while others create very few products before reaching equilibrium. Rarely are the products equal to the reactants at equilibrium. This ratio is called the equilibrium constant, and it is calculated by taking the concentration of the products divided by the concentration of the reactants. So here we have this K. The variable for the equilibrium constant is K, and it will have a different letters of subscripts like EQ here, for example, and we will talk about those in a moment. You take the concentration of the products. Concentration is molarity, which, if you remember, that is moles per liter. The concentration of all of the products, 1, 2, or 3, or however many products you have, multiply them together and put them in the numerator of the K expression. Then all of the reactants multiplied together in their concentration unit, multiplied together, is in the denominator. For this general reaction, A plus B turns into C plus D, where the capital letters represent the molecules or compounds, whatever species it is. You can see that we have C and D are in the products, are in the numerator, and the A and B are in the denominator. The lowercase c is a coefficient. If this lowercase c was a 1, then raising the power of c to 1 is the same thing. But if it's a 2, then you would be squaring the concentration of C before multiplying it by the concentration of D. And if this lowercase d was a 3, then you would be cubing the concentration of D before multiplying it by C. If there are greater products or a greater number of products, then the K value here will be greater than 1, and that's because the products are in the numerator. So if K is greater than 1, then that means there are more products at equilibrium. But if K is less than 1, then that means your denominator is larger and there are more reactants at equilibrium. And there's the answers to the fill in the blanks. There are many subscripts that you could place on the K, though all of these Ks are calculated the same way. Products multiplied together divided by the reactants that are also multiplied together. And don't forget the coefficients turn into exponents on each respective compound. So let's look at, we have KEQ. The EQ just stands for equilibrium. Essentially, all of these Qs are KEQs because all of these Ks are equilibrium constants. The K sub C means you have concentration of aqueous species in molarity. Again, most of these could actually be K sub Cs because almost all of these are calculated using molarity or concentration. The Ka, Kb, and Kw are Ks that we will look at in our acid-base chapter. The KSP, SP stands for solubility product, and it is for ionic compounds dissolving in water. And the KP is the only one that is a little bit different. It is still calculated as products over reactants, but instead of a molarity, we use the partial pressure of the gases in units of ATM. And you'll see that in the problems, it will give you the variables or the values in units of ATM. Let's look at this red highlighted box here. Liquids and solids are never included in any of these K expressions, only the gases and aqueous. This is very important. So on your notes, you should write this out and then highlight it, underline it, circle it, whatever it takes to help you remember that liquids and solids are never included in any of these expressions, only gases and aqueous. So now let's practice writing equilibrium expressions. When the question or problem asks for the expression, that does not mean calculating the value. You will not be plugging in any values. That will be the next example problem. So these are written as products over reactants. Our product is only one NO2 here, one substance, and we have a coefficient of a 2. So we need to turn that coefficient into an exponent. Then the reactant goes in the denominator. And there's the first problem done. Part B here, we take our products and put them in the numerator. You must include charges. In the reactant side, we have a liquid and we have an aqueous. If you remember, liquids and solids are never included in any of these expressions. So you just leave out the water molecule and you only write HF here. This next one is a KP, and the P stands for partial pressure, and we need to use ATM as our units for the values. So we can't use the square brackets, since square brackets specifically means molarity. So instead, we write this still as products over reactants, but we're going to use normal curved parentheses. We write a large capital P to stand for pressure, and then write the substance. So this is the pressure of carbon monoxide, or CO, and it's squared because the coefficient is a 2. Then we have the pressure of the oxygen molecule, and then in the denominator we have the pressure of CO2, squared again because of the coefficient. Here is an example of a KSP. Like I said, they are ionic compounds trying to dissolve in water. So on the reactant side, we have this ionic compound stuck together in a solid phase. And we only then have products because solids are never included. Let's look at this yet again. Liquids and solids are never included in any of these expressions, only gases and aqueous substances. So since the products are the only ones with an aqueous or gases, then we don't have a denominator in this K expression. You must include the charges on anything that has a charge. The oxygen, or the OH, this hydroxide, has a 2 coefficient, therefore it has a 2 exponent. And here's all of the answers written out nicely. Expression means the equation. Each of these written in red are the expressions. So when the problem asks you for the expressions, you write this out. You don't plug in any numbers. If the problem asks for the equilibrium constant, this means the value of K, and you do plug in your values or your numbers, and we'll do that next. All of these Ks are written products over reactants. All of these Ks include coefficients as exponents. All of these Ks only include aqueous and gases and never solids or liquids. All of these Ks, except for Kp, use square brackets, which means molarity. And remember, molarity is moles over liters. Only the Kp has parentheses, the curved parentheses, and this means partial pressure in ATM. Now let's do this problem. A system establishes equilibrium at 500 degrees Celsius in accordance with this chemical reaction below. And the following concentrations were measured. Calculate the value of the equilibrium constant, K sub C. In order to calculate the value, we must first write the expression, because the expression is the equation we can use to know how to plug in all of these values. So we have the product is NH3 squared because of the coefficient 2. Then we have nitrogen and hydrogen multiplied together in the denominator where the hydrogen value is cubed. Now we plug in our values and solve. See if you can do this. Once we plug in our values, we get this. So you have the nitrogen value is plugged in here, so that turns into this one. And then we have our nitrogen, sorry, that was the ammonia or NH3 value. Then we have the nitrogen value plugged in here. There is no coefficient on nitrogen, so there's no exponent on this value. And then we have the hydrogen value cubed. Now this can sometimes be tricky to type it into your calculator, so I would try a few times, pause the video, and see if you can come up with the answer here. There's a couple ways to type it in correctly, and there's numerous ways to type this in incorrectly, because your calculator can only follow order of operations. After a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius, it is found to contain 7.38 atm of hydrogen, 2.46 atm nitrogen, and 0.166 atm NH3, or ammonia. From these data, calculate the equilibrium constant K sub P for the reaction. K sub P is still products over reactants. We're just going to use the curved parentheses. So pressure of NH3 squared because of the coefficient, pressure of nitrogen, and pressure of hydrogen cubed. Plug in these values and see if you can solve for the equilibrium constant Kp. And here is the answer. Pause to see if you can type this into your calculator correctly if you didn't already. Now let's look at KSP, or the solubility product, a little closer. KSP is the equilibrium constant for ionic compounds trying to dissolve in water. And I'm saying trying because most of these are usually determined to be insoluble, though even an insoluble ionic compound dissolves a tiny bit. So when writing the chemical equation or reaction for each of these, H2O is left out, even though we talk about it as dissolving in water. So we're going to write out the reactions and equilibrium expressions for the following solid ionic compounds in water. Solid calcium carbonate, we're going to add the little solid here, and write a double arrow. We do not include the water molecule here because on the product side, we're going to show what this breaks up into and write their states of matter as aqueous, which means dissolved in water. We need to remember that calcium carbonate is made of calcium ion, which is a cation, positively charged, and carbonate ion, which is negatively charged. The calcium ion has a 2+ charge because it is in the second column on the periodic table. The carbonate ion is a 2- charge. The carbon and the oxygen are covalently bonded together and they do not get pulled apart by water. Water cannot pull apart covalent molecules. Instead, the whole carbonate ion together has a -2 charge and gets pulled away from the calcium ion. Each of these are aqueous. The KSP then is written as products over reactants. However, only the product side has either gases or aqueous substances. The reactant side only has one solid, and solids and liquids are never included. So we have calcium ion and we have carbonate ion. That is the first problem. Pause to see if you can work out the second one for lead chloride. And here's the answer for lead chloride. Lead chloride turns into 1 lead ion and 2 chloride ions. It is very important you write this as a 2 coefficient and not as a subscript, because this all by itself is in chlorine in its elemental form, which is always gaseous at room temperature, not dissolved in water. And this chlorine is toxic. We do not want to come in contact with chlorine at high concentrations. It could hurt you very badly. In fact, it could kill you. So you want to make sure you write it out as chlorine aqueous, 2 separate individual chloride ions with a coefficient of a 2. If that already wasn't clear enough, let's say it again. Ions wear their charges proudly. Whenever an ion has a charge, it'll be listed in the chemical reaction and must also be listed in the KSP. Because the chlorine has the coefficient of a 2, it gets the exponent of a 2 here. Now let's solve one of these for the value of KSP. Write the reaction and expression for solid AgCl in water. Start out, we're just going to do this part first. Start out like this, and I want you to pause and see if you can finish the chemical reaction and the expression for this dissolving in water. So here's the answer. Silver chloride turns into a silver ion and a chloride ion. Only the products have an aqueous or a gaseous substance, and so we have this as our KSP. Now the second part to this problem says, calculate the KSP for a saturated solution of AgCl dissolved in pure water if the concentration of chloride ions is found to be 1.34 times 10 to the -5 molarity. Pause to see if you can work this out. If this is too difficult, Here is a hint. Let's think about it. When silver chloride is the only compound dissolved in the water, the concentration of chloride ions must be equal to the concentration of silver. It's like if you were to break a pencil in half, you cannot get the eraser half without also getting the pencil lead half. So if you were to break apart 10 pencils and then you were told you have 10 eraser halves, you automatically know you also have 10 of the top half of the pencil or the pencil lead. So that means this value for the chloride ion is also the same value for the silver ion. When you solve it, we get this. Pause to make sure this makes sense to you. All right, let's do one more problem. Manganese sulfide dissolves according to this reaction. Manganese sulfide solid turns into one manganese ion and one sulfide ion. The KSP value is 5.1 times 10 to the negative 15. And the question is asking for the manganese ion concentration in a saturated solution of MnS. Pause to see if you can work this out. So let's start off by realizing that the KSP expression is written like this, and the value is given to us as this. And remember, you can't get a manganese sulfide ion without also getting you can't get a manganese ion without also getting a sulfide ion. So that means the manganese ion and the sulfide ion are equal to each other. So if you weren't able to solve it before, now pause to see if you can solve this. You just need to take the square root of the KSP because both of these are equal to each other.